عليكم ورحمة الله وبركاته. طلاب المرحلة الأولى، موضوعنا لهذا اليوم عندنا linear algebra 2 level 1 lecture 16 eigenvalues and eigenvectors. You know eigenvectors, you know vectors متجه, and eigenvectors will be the meaning in Arabic المتجه الذاتي and eigenvalues القيمة الذاتية eigenvalues قيمة ذاتية and eigenvectors المتجه الذاتي. First we take the definition. Let A belongs to Rn times n. A must be square matrix if V belongs to R n times 1 is non-zero and A times V is equal to lambda times V. For some lambda belongs to C if there is complex number, then we say V is an eigenvector with eigenvalue lambda of the matrix A. We explain the definition. Let A belongs to Rn times n, this square matrix, if V any vector in Rn times 1, V any vector in Rn times 1, the same, this is non-zero. This has to be non-zero. And if AV equal to lambda V, if I multiply A with this V is equal to lambda times V. For some lambda belongs to complex number, then we say that V is an eigenvector. This V will be say eigenvector, and this lambda we say it eigenvalue. This is definition of eigenvector and eigenvalue. Now take proposition. Let A belongs to Rn times n. Then lambda is an eigenvalue. Of A if and only if determinant of A minus lambda I is equal to 0. We say proposition, let A belongs to Rn times n, then lambda is an eigenvalue of A if and only if determinant A minus lambda I is equal to 0. We say P of lambda is equal to determinant A minus lambda I. This is P of lambda equal to determinant A minus lambda I, the characteristic polynomial. the characteristic characteristic polynomial. And determinant of a minus lambda I is equal to 0 is the characteristic equation. See, this is a proposition. Let A belongs to Rn times n, then lambda is an eigenvalue of A if and only if determinant for this determinant A minus lambda I equal to 0, this is true, then lambda is eigenvalue. We say the P of lambda is equal to determinant A minus lambda I, the characteristic polynomial. We say this polynomial تعددة حدود, this polynomial we say it's called characteristic polynomial, and determinant A minus lambda I equals 0 is the characteristic equation. We say this characteristic equation and this characteristic polynomial. So you have to know that. We take proof of this proposition. Proof. Suppose lambda is an eigenvalue of A, then there exists a non-zero vector V such that AV is equal to lambda V. This is by definition. If lambda is an eigenvalue for A of A, then there exists a non-zero vector V such that lambda AV is equal to lambda V. And this implies AV minus lambda V is equal to 0, of course. Okay, this is also implies A minus lambda here sub V, or lambda I here, lambda I, because this is still here I, lambda I. This is equal to 0. Notice that A minus lambda I V is 0, sorry, here 0 is equal to 0, of course. Thus the matrix A minus lambda I is singular. It's singular. This is page number 1. It's singular as the equation A minus lambda I x equals 0 has more than one solution. Has more than one solution. This implies determinant a minus lambda I is equal to 0. Look, this first direction, this is proof for this direction. If lambda is eigenvalue, so there is a vector v, non-zero vector v, such that av equal to lambda v, and this implies this. Also, this implies this, because we take v here and this is still here, I equal to 0. Notice that a minus lambda I times 0 equals 0, of course. Thus, the matrix, this matrix is singular, as the equation equal to 0. If this equation a minus lambda I x equal to 0, so this matrix will be singular. Has this has more than one solution. If this equation has more than one solution, so the determinant for this equation will be equal to 0. That means is this matrix is singular. This matrix will be singular because this has more than one solution. So if a matrix has more than one solution, so this, we say this matrix is singular. If this matrix is singular, that means the determinant of this matrix will be equal to 0. So now we get, if lambda is eigenvalue, so this determinant of lambda I minus lambda I will be 0. Conversely, prove the other side. Prove the other side. Suppose determinant of a minus lambda I is equal to 0. We suppose this. It follows that a minus lambda I, a minus lambda I is singular, will be singular, because determinant of this matrix is 0. Clearly, the system a minus lambda I x equal to 0 is consistent. That means متوافق as x equal to 0. If x equal to 0, so this system, there is no problem. 0 times this matrix will be equal to 0, so this is correct. That means this is correct. متوافق is a solution. Hence we know there are infinitely many solutions. In particular, so this is C. In particular, there exists at least one vector v is not equal to 0 such that a minus lambda I times v equal to 0, which means the vector v satisfies AV is equal to lambda v. Thus, v is an eigenvector with eigenvalue lambda for A. This finish the proof. Suppose determinant A minus lambda I equal to 0, it follows that this matrix A minus lambda I is singular because the determinant for it is 0. Clearly this system is consistent as x equal to 0. If x equal to 0, so this is correct. Hence, but this is singular. This matrix is singulars. We know there are infinitely many solutions because this is singular, so there are infinitely many solutions. In particular, بالأخص, there exists at least one vector. There exists at least one vector such that a minus lambda I times v equal to 0, which means the vector v satisfy a v equal to lambda v. Thus, v is an eigenvector with eigenvalue lambda for A. So this is finish the proof of this this is a proposition. Now take another proposition. This is page number 2. The following are equivalent for A belongs to R n times n and lambda belongs to complex number C. Number 1. Lambda is an eigenvector. Lambda is an eigenvalue of A. Number 2. There exists V is not equal to 0 such that AV is equal to lambda V. This is equivalent. Number 3, there exists V is not equal to 0 such that A minus lambda I times V is equal to 0. Number 4, lambda is a solution to determinant A minus lambda I equal to 0. Number 5, A minus lambda I V is equal to 0 has infinitely many solutions. So this is equivalent. If one of them true, then all others are true. If this first one is true, lambda is eigenvalue of A, then this is true and this is true and this is true, all of them is true. If this is true, so all of the other also true. If this anyone is true, so all others is true. Now we take example to know how we can compute the eigenvalue of a matrix. This example let A is equal to 3, 0, 8 minus 1. Find the eigenvalues of A. Find the eigenvalues of A. Solution. First, we compute determinant of A minus lambda I. Determinant A minus lambda I. That means this is equal to determinant of A minus lambda I. This is A. 3, 0, minus 8 minus 1. And minus lambda times I. Identity in one, what? 1, 0, 0, 1. And we subtract this, will be, this is equal to determinant out. This will be 3, 0, 8 minus 1. Here lambda times this matrix, lambda times 1 will be lambda, lambda times 0 will be 0, and lambda times 0 also 0, lambda times 1 equal lambda. And now subtract determinant. This will be 3 minus lambda, 0 minus 0, 0, 8 minus 0, 8, minus 1 minus lambda. And now compute the determinant for this. This is equal to, this is 0, so determinant for this equal to 3 minus lambda minus 1. This is determinant. And in the proposition, this determinant will be equal to 0. This determinant will be equal to 0. So this, we make this is equal to 0. The other line, the row, 3 minus lambda minus 1. This is equal to 0. So lambda is equal to 3, or lambda is equal to minus 1. So this is lambda 1 and this is lambda 2. And this is lambda 1, this is lambda 2. I think this is clear. If we want to find lambda for this eigenvalue for this matrix 3, 0, 8 minus 1, find the eigenvalues. Determinant A minus lambda I, this is, we find this determinant, this is A, the same this, 3, 0, 8 minus 1, and lambda times I identity will be 1, 0, 0, 1, and this determinant, this lambda move here, this is lambda, and this is 0, all of them, both of them, and this determinant will be subtract 3 minus lambda, and 0 minus 0, 0, and 8 minus 0 will be 8, minus 1 minus lambda. And now we compute determinant, because this is 0, so this is minus this will be 0, so this is minus 0 here, doesn't matter, and we make this equal to 0 because this is by proposition, so, and find lambda 1 and lambda 2. This is page number 3. We take another example. That a is equal to 1/2 root of 3 over 2 minus root over 3 1/2. Find the eigenvalue of a. Solution. The same determinant of a minus lambda I is equal to here determinant a what will be 1/2 root of 3 by 2, and here minus root of 3 by 2, and here 1/2 minus lambda I, this will be identity, and this b will be equal to determinant of 1/2 root 3 by 2 minus root 3 by 2 1/2 here, and this will be lambda 0 0 lambda, and now subtract. This will be determinant of 1/2 minus lambda, and this is root 3 over 2, and this is minus root 3 over 2, and this is 1/2 minus lambda. And if we take the determinant for this will be equal to 1/2 minus lambda times 1/2 minus lambda, minus this times this. Minus will be plus, because this is minus and the law is there is minus, so this is plus 3 by 4, and we make this equal to 0. Make this equal to 0. If we want to solve this equation, that means this will be equal to 1/2 minus lambda squared, this is the same, plus 3 by 4, this is equal to 0. So if we take to move this here, 1/2 minus lambda squared equal minus 3 by 4, and take root for this will be half minus lambda, and this will be root of minus 3, and this will be complex number. This will be complex number I. It will be I. That means minus lambda is equal to root 3. Okay, we can write root 3 over 2, but here plus, here plus minus, because root, and here plus minus I, and move here, this will be minus half, and times by minus 1, this will be lambda is equal to, this is still the same, plus minus over 2 plus here I plus 1/2. So lambda is equal to 1/2 plus minus root 3 2. So this is lambda 1 is equal to minus 1/2 plus root 3, here I, sorry, here I, 3, 2 I, and lambda 2 is equal to 1/2 minus root 3 over 2 I. This is lambda 1 and this is lambda 2. This is page number 4. I think this is clear. And now another example. Let A is equal to 2, 3, 4, 0, 5, 6, 0, 0, 7. Find eigenvalues of A. Solution. Determinant of A minus lambda I is equal to determinant of, this is A, 2, 3, 4, 0, 5, 6, 0, 0, 7 minus lambda I, identity in 3, 1, 0, 0, 0, 1, 0, 0, 0, 1. This is 3 times 3 because here it's 3 times, so I 3 times 3 this. And now move here lambda, this is equal to determinant 2, 3, 4, 0, 5, 6, 0, 0, 7 minus lambda 0, 0, 0 lambda 0, 0, 0 lambda. And this is equal to determinant of 2 minus lambda, 3 minus 0, 3, 4 minus 0, 4, 0 minus 0, 0, and 5 minus lambda, 6 minus 0, and here 0 minus 0, 0, 0 minus 0, 7 minus lambda. And determinant of this matrix will be, if we know this is zeros, so the determinant of this matrix will be times of this, just this diagonal, main diagonal, product of element of main diagonal. So this is equal to 2 minus lambda, 5 minus lambda, 7 minus lambda, and this is equal to 0. So this is, we get lambda 1 is equal to, lambda 2 is equal 5, lambda 3 is equal to 7. So this is values or eigenvalues. This is eigenvalues. And take a proposition. Let A be an upper or lower matrix, triangular matrix. Then the eigenvalues of A are the diagonal entries of A. Now this is without proof. Let A be an upper or lower triangular matrix. Then the eigenvalues for A of A, the eigenvalues of A are the diagonal entries. Diagonal entries, this is eigenvalues. So this is example for this proposition. This is upper triangular matrix. So this is value diagonal entries. This will be eigenvalue 2, 5, 7, because this is upper or lower matrix. This is page number 5. And now we take fundamental theorem of algebra. Fundamental theorem of algebra. النظرية الأساسية في الجبر. This is النظرية الأساسية في الجبر. Fundamental theorem of algebra. If P of X is an nth order polynomial, complex coefficients then the equation P of X equal to 0 has n solutions. Where n solutions where are some of the solutions may be repeated. That means that تتكرر. Moreover, if P of X is nth order polynomial, with real coefficients then complex solution to P of X equal to 0 come in conjugate pairs. It follows that any polynomial with real coefficients can be factored into a unique product of repeated real and irreducible quadratic factors. This is النظرية الأساسية في الجبر. Fundamental theorem of algebra. I will repeat this. This is just the state of this theorem. This is important theorem. If p of x is an nth order polynomial, if this is p of x nth order polynomial, complex coefficients معاملات complex, then the equation p of x has n solutions. Then this equation p of x equals 0 has n solutions where some of these solutions may repeated, has n solutions where some of these solutions will be repeated. Moreover, if p of x is nth order polynomial with real coefficients, here if this is real coefficients, then complex solutions to p of x come in conjugate pairs. This is conjugate pairs. You know conjugate pairs, x plus iy is equal to conjugate x minus if z is equal to x plus iy, then z conjugate, this is conjugate equal x minus iy. This is will be comes in pair of come in conjugate pairs. It follows that any polynomial with real coefficients can be factored تتحلل نحللها ممكن أن نحللها into a unique product of repeated real and irreducible quadratic factors. ممكن تحليلها إلى حاصل ضرب العوامل الأولية. This is page number 6. And we take, this is a proposition. If A belongs to R n times n, then A has n and A has n eigenvalues. However, some may be repeated and or complex. If A is R belongs to R n times n, then A has n eigenvalues. If A belongs to R n times n, then A has n eigenvalues, the same this. However, some may be repeated or complex. Some of them may be repeated or complex. Proposition. The constant term in the characteristic polynomial p of lambda is equal to determinant a minus lambda I is the determinant of A. This proposition mean that the constant term in the characteristics, this is will be equation by lambda. Will be equation by lambda. The last term without lambda. So the last term is the determinant of A. The last term is the determinant of A. Proof. Suppose the characteristic polynomial P of A has coefficients Ci. That means P of lambda is equal to determinant of A minus lambda I, and this is equal Cn lambda is n plus Cn minus 1 lambda n minus 1, and so on. This is plus 2 C1 lambda plus C0. This is the last one without lambda. Notice that if lambda equal to 0, then then A minus lambda I is equal to A. Hence P of 0, if we substitute here 0, this is all of them will be 0, just this equal determinant of A, and this is equal to Cn 0 is n plus all of them C1 times 0, C1 here plus C0. Thus determinant of A equal to C0. This is finish the proof. This is page number 7, and there are another proposition. Zero is an eigenvalue of A if and only if A is a singular matrix. This is without a proof. If A 0 is an eigenvalue of A if and only if A is a singular matrix. If A is a singular matrix, so 0 is the eigenvalue of A. Proposition. If A belongs to Rn times n, then A has n eigenvalues. Lambda 1, lambda 2, until lambda n. Then determinant A is equal to lambda 1 times lambda 2 until lambda n. So this is also without proof. Now real vectors, eigenvectors. Example, let A is equal to 3 1 3 1 find eigenvalues and eigenvectors of A. Solution: determinant of A minus lambda I is equal to determinant of 3 minus lambda 1, here 3, here 1 minus lambda. So this will be equal to 3 minus lambda times 1 minus lambda minus 3. This is equal to lambda squared minus 4 lambda, and this is equal to lambda minus 4. So this is equal to 0, and we find implies lambda 1 is equal to 0 and lambda 2 is equal to 4. Now try to find eigenvector with eigenvalue lambda 1 is equal to 0. Let u1 is equal to uv. Denote the eigenvector. So A minus 0 I u1 is equal to, this is A 3 1 3 1 times uv. This is equal to 3u plus v and 3u plus v. This is equal to 0. Make this is equal to 0. And this we get 3u plus v equal to 0. Also 3u plus v equal to 0. So this has infinitely many solutions. This implies v equal minus 3u. So we can write u1 is equal to u and 3 minus 3u. And this is u out. This is 1 minus 3. So this is v depend on u. We can take any point for u, so we get the this is eigenvector for 0. And this is page number 8. And A minus 4, this is for lambda, second lambda 4, that this is for 0. This is here for 0 vectors, and here now find it for 4. u1 is equal to A, this is 3 1 3 1 minus lambda, this is here 4, this is 0 0 here 4 times, this is times uv, and this is will be equal to 3 minus 4, this is will be minus 1, and 1 minus 0 is 1, and 3 minus 0 is 1, and this is minus 3 times uv. And this will be equal to minus u plus v, 3u minus 3u, sorry, 3u minus 3v is equal to 0, 0. And we get u2, so this is u2 for lambda 2, u2 is equal to, here we get u is equal to v, so u2 equal u, this means equal to 1, 1. So any point for u, we get the eigenvalue. This is an eigenvector for any u belongs to R, such that u is not equal to 0. I think this is enough for today. Thank you very much. Goodbye.